Okay, let's try this and not the complicated way.
You just do,
So I want to evaluate the circulation over a curve C of 3y minus e to the sine x dx plus 7x plus the square root of y to the fourth plus 1 dy, where C is the positively oriented circle of radius 9. Yes? Okay. There are two ways I could do this. One of them would suck.
yeah.
What's the one that sucks?
To do it like that.
Yeah, to leave it like this, right? I could parameterize the curve C. I could evaluate this thing at my parameterization, right? Evaluate dx and dy. Get some horrible business, right? Multiply it all out. Integrate from 0 to 2 pi, presumably. Yeah? That would be sad. Don't do that. Instead, use Green's theorem to rewrite this thing as what? The double integral.
Partial q over partial x.
Okay, so I need to think partial of q with respect to x. So which thing's q?
7x plus the square root of y.
This jazz is q, right? 7x plus stuff. Why don't I care about this stuff?
Because stuff is wise and it goes away.
Because stuff is y's, and when I differentiate with respect to x, right, it drops out. So your result, differentiating 7x plus stuff,
Is 7
is 7.
minus 3.
Okay, and then I should be subtracting, and this guy should be partial of p with respect to y.
I'm trying not to.
It's fine.
It's just making me hungry too at the same time.
All right.
I got Roman.
Partial of p with respect to y, I get 3. Because p is the first thing there, right?
Yeah.
Okay, so that's p. And then I'm integrating this d
dA.
area. And what's your double integral over?
D.
Yeah, some region D, which is really a disk, right? And it's a radius now.
Oh, radius. I didn't kind of want.
Cool. So I get what?
The double integral
Double integral of 4
r dr d theta.
r d theta.
Yeah.
Okay, and your r's go from
0 to 9.
0 to 9, and your thetas go from
0 to 2 pi.
0 to 2 pi. None of that stuff depends on theta, right?
No.
Is that? So what's your integral with respect to theta? What's that going to kick for you?
It's gonna. Oh, are you talking about the splitting?
Yeah, remember the trick, right?
Okay, so 4. Because I'm gonna take that.
Okay, I'm going to get a 4 out times the integral from 0 to 2 pi
of d theta.
of d theta
Multiplied by
times the integral from 0 to 9 of
r dr.
r dr. Did that split make sense? Do you guys remember that trick?
Yeah.
Right, that's there's no thetas in here. So this stuff's all constant with respect to theta, so I can take it out. And then the 4 I can take out of that. Cool?
Yeah.
And then what are your bits here? What do you get?
You're gonna
You
get
4 times
2 pi.
2 pi times
81 over 2.
81 over 2, which is
1.
4 pi times 81.
Yeah. 324.
Which you might notice, what? I could have noticed something a ways ago. I just did all this integration, right?
Yeah.
Okay, but right here, this thing, this was 4 times the double integral over a disk of 1 the area, right? That's going to give you the area of the circle.
Yep.
So I got
4 and then
4 times pi times 9 squared. So maybe I did it that way, maybe I did it the other way. Either way, right, either execution of the area integral is how much easier than the line integral would have been?
A lot.
Lots, tons, right? Many, many bajillions of times easier.